Mean squared error. In the last lecture, we were learning about regression loss functions. Here, we are going to look into the first regression loss function called as mean squared error. You can call it as mean squared error or mean squared loss. What we are going to see is what exactly is this particular loss function, when to use this loss function, and what are the advantages that you get when you are using mean squared error, right? This is a very widely used loss function or error function. Let us see what this is. First of all, let us say you have a data set which is having a total of n samples, okay? And each of the sample will be like xi, yi. So xi is your given input and yi is the actual output, or you can say this is the true value. What are you going to do? Through your model, you are going to provide input xi. Your model will process this input. It will finally provide the output yi cap. Yi is the actual value, true output that is required. Yi cap is the predicted value or whatever is produced by the model. That is what you are calling as yi cap. Then what is error? Error is the difference between yi and yi cap. This is what we want to identify. How much is your prediction yi cap deviating from the true value called yi? This is what is the error. So in the last lecture already we had discussed why you can't simply use something like yi minus yi cap. Something very simple. Why can't this be used? This we already discussed. Here we are going to see what is mean squared error doing in order to manipulate it. Okay. As the name suggests, it is the mean of squared error. If you see this as the error, that is the deviation of yi from yi cap, or you can say the deviation of predicted value, which is yi cap, from the true value, which is yi. This is what you're calling as error. Then what is squared error? From mean squared error, I'm just trying to make sure that you understand this terminology correctly. You have the error now, which is yi minus yi cap. What is squared error? If you simply square this value, this is called as squared error. What about mean of squared errors? That is what you're calling as mean squared error. When you want to take mean of any values, let us say instead of these n values, you have some particular value xi of which you want to take mean. So there are n values and ith value is xi. You want to take mean of all those values. How are you going to take? Your mean will be 1 by n sigma I is equal to 1 to n xi. This is how you are going to find the mean or average of n values. So if this is your squared error for the ith input, how are you going to get mean of the squared errors in case there are n points in the data set? The same way you did mean here, you are going to do mean of this value 1 by n sigma I is equal to 1 to n yi minus yi cap. This value is called as mean square error, MSE. This will be 1 by n sigma I equal to 1 to n yi minus yi cap the whole square. So this is the error term. This is the squared error. When you squared the error, then you took the mean, which gave you mean squared error. So this is how you want to understand this particular loss function. The next question is, why are you squaring here? What is the advantage of squaring? Why do you want to introduce a mathematical work which is additional work over the error you are having? This is the first thing you have to understand. See, simply understanding the mathematical formula doesn't do anything. You have to understand why is this formula used, what is the significance of this formula, how does this add any statistical importance. Once you understand these things, then it's easier for you to logically be clear about what is this particular loss function. Also, this will help you to identify where to use it. Okay. So first of all, let us see why are you squaring the term here. The first advantage of squaring is Positive and negative errors, these will cancel out each other. Otherwise, what happens is, if you simply use yi minus yi cap, if in one case you are having an error of plus 2 and another case you are having an error of minus 2, when you finally add all these errors, both these will cancel out. But actually both these are errors. There is an error of plus 2 on one example and minus 2 on another example. And when you are adding, errors should actually add up. But here, because one is positive and the other is negative, what is happening? It is getting cancelled out to 0. In order to avoid that, if you square the term, that is, in case your yi minus yi cap is plus 2 in one case and minus 2 in the second case, if you square both these values, this will be plus 4, this will also be plus 4, which means at this point, if you add these values, this will add up to 8. So this is how positive and negative values do not cancel each other once you square it. This is the first advantage. What is the second advantage of squaring? Second advantage is, whenever you are having a large error, those larger errors will be penalized heavily. Why should this be done? This should be done because, let us say you are doing some sort of a darting game. One person, this is your dart board, you want to actual aim is the central point, this one. But in case your aim is not so good, you may be, let us say, hitting somewhere over here or maybe somewhere over here. But let us say there is some person who is actually, he only managed to hit maybe at this point, somewhere over here. Instead of the actual darting point, one particular person managed to hit here. While you are in training phase, what you want to do is, when you are having the hits somewhere near the actual darting point, those should be penalized in a lower value, that is not so heavily. And when you are having very off target values, when your actual darting point is here but you are hitting here, which is way outside, you should actually penalize these very heavily, so that next time your model won't try anything of this kind. So in order to do this, what you do is, when your model's prediction yi cap is very far from yi, which is the actual true value, then those far values should be penalized even higher. This is where squaring really helps you, because if you are off by, let us say, 1 point, that is, if your actual value yi, the expected value is 5, but let us say you predicted 6, your yi cap is 6. If this is the case, the error is plus 1 or minus 1, whatever you may say. If you square it, it will be 1 only. But if your error is very large, let us say this is 15 instead of 6, which means the difference is 10. When you square it, it will be 100. So what happened here? If you want to have a total error of 100, you may have to make this error 100 times. But this large error, if you make one time, an error of 10, if you make it one time, it will add up to a total error of 100. Which means when the error was higher, that is 10, you penalized it heavily, not actually 10, you penalized it by 100. But error is 1, at that point you penalized it only by 1. So the second advantage that we were talking about is that when you have a larger error, it will be penalized heavily. This is what you will get with squaring. Third point, let us see what is the next advantage. Next advantage is, we already discussed that whenever you want to improve your model, you have to take the gradient of this loss function. That is, you should be able to differentiate this loss function, and then this gradient helps you improve. We'll learn it in detail when we reach gradient descent. As of now, just understand this. When you try to differentiate, when it is a squared value, what happens? It will be differentiable everywhere. So because of this, it is useful for gradient descent. This is the third point. So there is one more thing, which is that squaring is generally easier to compute. But then you can ask, if you don't square at all, that's even easier. So compared to other loss functions, simply taking square is an easier to compute thing, right? So these are the major advantages of squaring. The next thing is, I told you whenever you choose a loss function, it should have a statistical significance. If it has a statistical significance, then it is logical. So what is the statistical significance of this MSE? Statistically, how will you state this? You can say MSE represents the expected squared deviation between the predicted value and actual value. So this is the statistical significance. You can say it has expected squared deviation. One more thing you want to see is, let us see how you are actually finding the gradient. I simply told you here that it is differentiable at all points. Let us see what is the gradient in this case. So this will give you a bit more insight. That is why I want to do this. See, in machine learning, these loss functions, you should at least know how to find the gradient. This is very basic. That is why I'm doing this in this particular lecture. We'll take this MSE loss function, loss. Let us just consider one point for now. That is, here we considered n points. If you take only one point, then the loss will be y minus y cap squared. This will be the loss. What if you take gradient of this? If you take gradient, how do you take gradient? Let us say you want to take with respect to y cap, which is the predicted value. Then del L by del y cap. What will this value be? This will be minus 2 into y minus y cap. How did I get this? Because if you take gradient of this, that will be minus 1 because y cap is having a minus sign. That multiplied with this 2 will get minus 2. So that minus 2 came here and y minus y cap. This is the gradient of this loss function. So if you take the full data set, what happens? For all the n points, if you take del MSE, that is MSE is this particular value. If you do this by del yi cap, I'm taking gradient with respect to one particular predicted value. Okay. If I take this, what happens? If you do this, in this summation term, there will only be one particular term which is corresponding to yi. So if you take that term, it will have a minus sign on the yi cap, which means when I take gradient, it will be this 2 will come out. So minus 2 by n into yi minus yi cap. This will be the gradient of the total MSE. What does this gradient tells you? This tells you how to adjust the predictions in order to reduce error. This is where gradient is helpful. So in detail, we'll see in gradient descent lectures how exactly we are using. For now, understand that this gradient decides how much this model should change the value in the next iteration or in this particular step of training. How much should it change its predicted value? This is what kind of you can understand like this. This is what gradient will decide. So one more thing. When do you actually use this mean squared error? This is very important. That is, you should know where to use it. You know what is mean squared error. Under what condition? When do you exactly use mean squared error as your loss function? You know the loss function, but you don't know where to use, then it's a problem. So the first thing is that whenever you want larger errors to be penalized heavily, if this is to be done, keep in mind whenever you have a situation where you have off-target values, larger errors, those are to be penalized heavily, then you will always use mean squared error as the loss function. Second point is, whenever you are assuming Gaussian noise. What is Gaussian noise? So Gaussian noise, you can generally see it as a bell curve. That is, if your noise forms this sort of a bell curve, which is having a peak and it is falling off towards both the sides, this is a Gaussian. So whenever it is a Gaussian noise, or you can say errors are normally distributed, under this case, you generally use mean squared error. So why is this done this way? Because regression with MSE, this can be seen as MLE, the maximum likelihood estimation under Gaussian noise. That is what we'll see in the coming lectures. What is Gaussian noise, what is Laplace noise and all very clearly. For now, understand that if it is Gaussian noise, then generally mean squared error is your go-to loss function. Okay. So if you believe your data has Gaussian distributed noise, then minimizing MSE is the statistically optimal choice. That's what you can say. Then one more thing is, this is commonly used in what cases? One is in linear regression. Generally in linear regression, you use mean squared error as the loss function. Then many times in neural networks, you make use of this. In deep learning applications, you make use of this. So as you go forward, you understand about other loss functions. You'll be very clear about where to use mean squared error and where to use the other loss functions.